Okay, friends, let's go ahead and look at this. We're going to talk a little bit about exponential functions and what they look like. So, generally speaking, there are a couple of ways you could think about exponential functions, but one way to think about it would be y equals ab to the x. And so, let's have a discussion about that first. I'll zoom in. What happens if x is 0? Then you have y equals ab to the 0. Well, b to the 0 is just 1, so then y is a. So we'll have a point 0a. Oh, that's the y-intercept. And then the b value, let's make a table. If I plug in 0, I get a. If I plug in 1, I get a times b. If I plug in 2, I get a times b twice. If I plug in 3, I get a times b 3 times. So the b is the thing you're multiplying by every single time. Now, let's think about this. If I'm multiplying by something every single time, under what conditions or what values of b will that quantity be getting bigger? And under what conditions will that quantity be getting smaller? Now, you should be able to say, okay, well, if I multiply by something bigger than 1, then my quantity will be getting bigger each time. If I multiply by something between 0 and 1, my quantity will be getting smaller. Think of multiplying by half every single time versus multiplying by 2 every single time. So for exponential growth, that will occur when b is greater than 0. For exponential decay, try again, greater than 1. Exponential decay, b will be between 0 and 1. Notice that you don't want b to be a negative. If b is a negative, then we're not creating a function that we're going to enjoy. It's not going to be something that will have properties that we can play with for our purposes. Oftentimes, exponential growth will look something like this, and exponential decay, I don't know why my axis didn't show up, will look something like this. All right, so let's look at these. You should be able to decide which of these tables shows growth or decay by just kind of looking at them and playing around with the numbers a little bit. So feel free to pause and take a moment and process and think about what's going on. So I'm going to write your turn. So think for a bit. Pause this, think for a bit. If you haven't paused it, you should pause it. Okay, I'm going to assume you paused it and came back. When I look at this one, I'm seeing this goes up 6. This goes up 6. This goes up 6. Oh, this is just a linear function. So my equation for this one, if I put it into slope-intercept form, will be I'm going up 6. That's my slope. And then my y-intercept is 3. So that one is linear. That is not exponential. That is linear. Now, when I look at this table, that looks like divided by 5. And divided by 5. Divided by 5. Divided by 5. And if I'm dividing by 5 every time, that's the same thing as multiplying by 1/5. So I could also say, or multiplying by 1/5, multiply by 1/5. So if I take my initial quantity, because that's a 0, I'll consider that my initial quantity, and I multiply by 1/5 every single time, that will be my equation. So that's going to be, let's see, now let's think. Is that growth or decay? Well, my b value is 1/5. That is between 0 and 1, and that means we have decay. When I look at my next table, that's times 3, that's times 3, that's times 3, and that's times 3. So that means I'm taking my initial value, I'm multiplying by 3 every single time. So that's my new equation for that curve. And 3 is greater than 1, which means we have growth. If you struggle to making the equation, that's okay, but it's about patterns. So if you start looking at patterns, it'll make some sense to you. All right, now, does the table show exponential growth or decay? So you should pause me, and you should think about this, and you should consider what's going on. And once you've unpaused me, you should figure out that we're dividing by 4 every time, which is the same thing as multiplying by 1/4. So since we're multiplying by 1/4, that is exponential decay. And just for fun, let's write an equation. So we start with 120. We're multiplying by 1/4 every time to the x. And that's my equation. That's all it is.